so this was the last thing we did. So new section, and this section would be called, so section 4.4, which is titled, let's see, spanning sets. And linear independence. Okay, so the idea of spanning sets and linear independence is going to be very important. And I think it's also one of the more, I think one of the more abstract things that you guys will see. So basically the idea is this. I think I already introduced the notion of linear independence at like about like 2 chapters ago or something like that. So again, so remember, I had a set of vectors, and I said a vector is linear. It's a linear combination. Sorry, not linear dependence, linear combinations. A vectors are linear combinations of another set of vectors if you can like add them with some scalars and give that vector back, right? So I kind of put it side to side, like these are the atoms of the vector B, right? So we're gonna now dive in and see what that means a bit more. So again, so let us define something. So a vector B in the vector space, say B is called a linear combination of the, let's say, vectors u1 all the way to un if it can be written as B is equal to C1 U1 all the way to Cn Vn for some constants in your field, right? In this case, it'll be real numbers or whatnot. So again, so I always said this V is made out of these vectors U, right? And you can think of these like these. This vector V is made out of these vectors U, right? So that's how I think of it. Okay. So now let's investigate some I guess examples, right, out of this. I mean, this definition could be very abstract, but we can illustrate with some examples now. So let us illustrate with some examples. Okay. So I mean, one such example we can say is the vector, let's say 2, 1 is a linear combination of say 1, 0 and 0, 1. Since we have what 2, 1 is going to equal 1, 0, 0, 1. Add them together. So what constants would give me this? Well, if I put a 2 here and a 1, and I just put a 1 here, that would give me the vector 2, 1, right? Okay, so that's nice enough, but now you can ask the question, is every vector a linear combination of any set of vectors? And if so, if not, then how can you tell if it is, right? So is every vector a linear combination of other vectors, or of a given set of vectors? Again, U1. The answer is no. However, we can figure out if something is a linear combination. But we can figure out if a vector is a linear combination of a given set. So let's see. Okay, so how do we do this? Well, in let's say the vector space Rn, there's a nice, neat way to do this in Rn for the vector space Rn. Now, in every other vector space, this method won't work. So, in a vector space Rn, we can use augmented matrices and reduce row echelon form. Okay. So let's see how we can do this. So example 4.41. Write the vector, say W, which is going to be the vector 1, 1, 1, as a linear combination of, let's say, of vectors in the set S, which is going to contain the vectors 1, 2, 3, 0, 1, 2, -1, 0, 1. Okay. So how do we do this? So remember, what does it mean to be a linear combination? Well, from this definition I gave here, we want basically this. So we want to find our CIs in this expression, right? C1, 1, 2, 3, plus C2, 0, 1, 2, plus C3, -1, 0, 1, right? This is the definition of linear combination. We want to find constants C1, C2, C3 that makes this true. But if you remember, for vectors in Rn, I gave a theorem in chapter 2 or so of equivalent forms of linear systems. If you remember, one of them was actually this form. So you can use the augmented form. So we can use the augmented form. And what is the augmented form? Well, you're gonna put, okay, so let me put this on the next page. So we're gonna put this guy on the constant side and all of these on the like left hand side of that. So it's gonna look like this. So you're gonna have 1, 2, 3, 0, 1, 2, minus 1, 0, 1, and 1, 1, 1 here. Okay. And then RREF this. And if you RREF this, we get the following row reduced echelon form. So we get 1, 0, minus 1, 0, 1, 2, 0, 0, 0, and then over here you're gonna have 1, minus 1, 0. Okay, so now from here, what do we have? Yeah, I can go back to the slide. So in that augmented form, so okay, so once you have this augmented form, what is this telling me? Well, what it's telling me what the solutions are for C1, C2, and C3, right? Now notice in that augmented form, once I go back to it, that system's gonna have how many solutions? Right here. Infinite, right? There's infinitely many solutions. So notice that there isn't just a unique constant C1, C2, C3 that makes this true. So here we have infinite solutions. And the solutions, again, so each one of these represents C1, C2, C3, right? So if you solve for this one, you get that C1 is going to equal 1 plus C3. C2 is going to equal minus 1 minus 2 C3. And then C3 is free, right? To answer the question at this point, all you have to do is pick a number for C3. And you'll get C1 and C2 from there. So let's pick, I don't know, what's an easy one? Pick 1. So pick C3 equal 1. That means your C2 is going to be C1. C1 is going to be 2, and then your C2 is going to be minus 1 minus 2 would be minus 3, right? Yeah. Right. Yeah. That's correct. Yes. Okay. So these constants would make it a linear combination of the other vector. Yeah. Oh, that doesn't. Okay. Okay. All right. So the simple idea, very powerful, of what we're going to do next. Okay. So just a few remarks. Let's see. So so now that you guys see how we do find the linear combination of vectors, do you guys think now when will a vector not be a linear combination of a set of vectors? What would happen to your matrix? You would have an inconsistent matrix, right? If you have inconsistent, that means your vector can't be written as a linear combination of the others. If you have infinite many solutions, just means that you do have a solution, but you have infinite to choose from. If you have a unique solution, there's only one way you can write that vector as a linear combination of others. So here, let's mark that. So if matrix is inconsistent, then vector, I wrote C3 twice. Oh, I did. Should be C2. If matrix is inconsistent, then vector cannot be written as a linear combination of the given vectors. If consistent, then you can, right? So that's, I mean, that's as simple as it gets. There's nothing more than that. Okay. Okay, so now that we understand what it means to be a linear combination in some sense, now let's talk about what it means to be a spanning set, okay? Okay. So the idea of spanning set is this. The span of a given set of vectors. So if let's say I gave you vectors u1 through un, right? And I told you take all linear combinations of them, meaning add them together with scalars in front and change the scalars with every real number or whatever field you're in. The set that produces, all those vectors that it produces, is called the span of those set of vectors. So it's every possible linear combination that you can get out of a given set of vectors, okay? So let me just, I guess, illustrate that a little bit more by defining it. So let's see. So if given a set S of say U1, UN, the span is the collection of all possible linear combinations. Meaning, if you do this, oops, that's not a vector. So take all possible things that look like this from that, and then put them in a set, and that thing is called the span. Okay. So let me formally define that now. All right. So let's see. Would that be? Yeah, I think that's fine. So definition. So let S equal say U1 all the way to UN be a subset of V where V, where this is a vector space, right? Okay, so let's take the subset. The set of all possible linear combinations of S is called the spanning set of V, or of the vector space. Okay. So in other words, this is the sorry. So or sorry, this is called the span. This it's called the span. This of S. I was getting ahead of myself there. And is denoted span of S. Okay. So again, what is the span of S? So span of S is just equal to the set of all linear combinations such as CIs or in this case real numbers, right? So take all linear combinations. This is called span of S. Okay. What's a good example? I'm trying to like, I guess, illustrate this with a good example. Yeah, this is actually a good example. Okay, let's illustrate. Let us illustrate with an example. Okay, so consider the vector 1, 0. Okay, so let's draw this on the plane right here. So we have this and this. So y, x. So this vector right here is going to look something like this, right? Or this, what I guess this part right here is 1, and yeah, so it has length 1 and it's on the x-axis. So what is the span of? So let's take the span. Let's consider, and the span of 1, 0. So what is the span? Well, the span of 1, 0 is the set of all linear combinations of 1, 0. In this case, it's going to be in the real numbers, right? Okay, so what happens if I multiply this vector by any number C1? What's going to happen to it? So let's say I multiply by 2. What would happen to the vector in the picture if I multiply by 2? Yeah, it would be twice as long. So it would be like this now, right? Like it'll be twice as long. Okay, so what if so now if I multiply by -2, it'll just point the other direction, right? So now take the set of all these vectors, multiplying with every single real number. What picture would I draw in this case? Huh? Not a circle. The what? Parallelogram, not quite. All the lines at the same. Yeah. So it'll be a line. So right, because it'll be all of this line. Right, because the vector is just gonna go on this line. If I make it twice as long, it's just gonna all the vectors are gonna lie on this line, right? So, so this right here, in this case, the span of so this would be the span of 1, 0. It will be the x-axis, right? Okay, perfect. So now you guys kind of see what the span is, at least in this example, right? So the span is going to give you, if you think of it in Rn as space, some type of space in your region. So for example, if I would have taken I don't know 1, 0, so 1, 0, 0, 0, 1, 0, 1, 0, and then take the span of that and plot it in 3D space, that would have given me a plane. All right. So the span in that case would have been a plane, and so on and so forth. Right. So again, so just keep this in mind. What? So y equals 0. Yeah, you can think of it the line y equals 0, but really it's just this line, the x-axis, right? So it's the set of all, it's basically this entire line. This is what the span is. Okay, perfect. So now that we have some type of handle on span, let us now go on to the notion of spanning set. So by the way, do you see how this vector 1, 0? Why? No, it wouldn't just be 1. So remember, so look right here. I called this the set of all vectors 1, 0 times C1, where I take C1 to be every real number. So I take every real number, not just one. I take all of them and multiply, and then so like this. Watch. So the set can consist of 2, 0. It'll be 3, 0. It can be 1/2, 0. It would be pi 0. I mean, it's all the real numbers, right? Yeah, exactly. So that's what I was going to get to the next thing. So do you guys see how here the entire x-axis is that span? So what we would say is that this set 0, 1 is the spanning set for the x-axis. So if every vector in a certain space can be written as a linear combination of those vectors I give you, then that set S spans that vector space. In this case, it's the x-axis, but I'll make that a little bit more precise. Okay, so definition. So again, let S again be a set of vectors u1 to un. Let S be a subset of a vector space, say V plus, right? Then S is called a spanning set. Yeah, so is called a spanning set of V, or of the vector space V plus this thing, if every, so this is the key word right here, so if every vector in V can be written as a linear combination of those vectors in S, as a linear combination of the vectors in S. Okay. In this case, or I guess we can say, we then say S spans V. Okay. So again, what's the idea? If I give you a vector space, right? And I take a subset of this vector space. Pick any vector in V. If I can write any vector in V as a linear combination of that subset that I just took, then that subset S is called a spanning set. So and we say it spans. So again, why are we talking about this? Well, you'll see the punchline at the end, but just think of it this way. No, pick a vector in V, if I can write as a linear combination of the vectors I picked out of, in S, then S is said to span all of V, right? So by the way, if you ever guys wondered why we call 3D space three-dimensional and 2D space two-dimensional, we define it exactly this way. So a vector space dimension is actually dependent on how many elements are in this S right here. Well, I mean, it's not just, I mean, you would have to actually get the basis, but this is one notion of how we can define dimension. But anyway, so let's go back now to another example. So let's look at spanning sets now. So example, I don't know, 4 point. How many examples did I give here? One. Okay. 4.42. So consider. So what is this? Okay, so you can say, what is the spanning set of the vectors, say 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. Okay, so let's just look at it then, right? So what is, so let's analyze C1 times 1, 0, 0 plus C2, 0, 1, 0 plus C3, 0, 0, 1. All right, guys, so what picture with this, so this is in 3D space, by the way, so this is 3 components. What do you think this would draw, the span of these three vectors? What would it draw? Not a line in this case. XYZ, what do you mean XYZ? XYZ what? I mean, you're like, I think you're gonna say it, but yeah. The XYZ plane, yeah. So it isn't just gonna be straight lines. So it's actually gonna. So if you draw your XYZ plane, so this is Z. Say this is X and this is Y. This thing is just gonna be all of that. All of it. So it's literally going to be all of this stuff. So it's going to just be the entire 3D space. So span, and you can see this, right? Because if you actually combine this, so combine it, like combine the vectors all together. So if I write it all out, I'm just going to get C1, C2, C3, right? Can I choose C1, C2, C3 freely? I mean, if I'm considering the spanning set? Right, I can, right? I mean, right here, I mean, this is how I did it for this guy. I chose C1, C2, C3 freely, right? So since I can choose them all freely, I can get any vector in 3D space, no matter what it is. So I can pick the vector, I don't know. Let's say I wanted the vector, I don't know, pi, e, and like 3. What would C1, C2, C3 be? Well, C1 would be pi, C2 would be e, and C3 would be 3, right? So no matter what vector I pick in my plane, XYZ plane, I'm always going to be able to find a C1, C2, C3 to make it. So in this case, we say that the span of S is just all of R3. Okay. Now it's important to note, well, I guess you can say this S spans all of R3, and this is how you can write it as well. I just want to note that these things right here, these vectors I chose, we'll talk about them later, but these are what you call the basis. No, it wouldn't work for every spanning set. So I mean, if I were to take, like, for example, if I just took S equal 1 0 0 0 1 0, and I said, and that's it, this wouldn't span all of R3. This would actually just span the XY plane. So it would only, so this, like, if you see the XY plane right here, that part, that span of those two vectors would just be that part right there. It wouldn't be all of R3. Yeah, R2. But since we're doing three components, it would be just this plane, the plane where it happens to be the XYZ plane. But you can't say this. You definitely cannot say this equals R2 in this case. And there's a reason why. It's because this has three components. It isn't just, if it had only two components, you can't say that. But I guess you can embed it into the XY plane, so it's, I guess, isomorphic to it. But in that case, you would say this is isomorphic to R2, and we would talk about that later. But don't say it's equal to R2 because it's not. But yeah, so S, in this case, span of this S would just be that red plane that I drew on the XY plane. But yeah, so what was I? Oh yeah. So these three vectors, the ones that have 1 in one position and zeros everywhere else, are called the standard basis for that vector space. So for R3, it would have three components. If you were to consider Rn, you would have n of these vectors with 1 and zeros in the rest of the, so like this. So for Rn, it'd be like this. 1 0 all the way to 0 0 1 all the way to 0, and so on and so forth. You get 0 1 0. So these are the standard basis vectors for Rn, right? So what that means is that this thing could, these vectors can can span the entire space. And we'll talk about basis again later, but for right now, let's go to another example. So as you can see, we've only been doing vectors in Rn, but what's stopping us from doing vector spaces other than Rn, right? So remember how I told you we're gonna have to remember those vector spaces, the functions, polynomials, and all that. Well, this is one part we're gonna use it. So example 4.4.3. So let S be equal to, let's say, 1x squared be a subset of the space of polynomials of at most degree 2. So if you don't know what this is, remember it's just the set of all polynomials. So a0 plus a1x plus a2x squared, such that all those are real numbers. In this case, I'm going to consider them in real numbers. Okay, so that's what this means. So let us see if this thing actually spans. So does the let's say, does S span P2? So what do you guys think? So what do you think you would have to do to see if it spans P2? Well, remember, yeah, it does span it, right? It might be a kind of a silly question, but so remember, for it to span P2, what has to be true? That means if I take any polynomial of the degree 2, like something that looks like this, I should be able to write it as a linear combination of these things, right? Okay, so let's just look at an example. So let's say, just consider, I don't know, 1 plus 2x plus 3x squared. Can I write this as a linear combination of 1x squared? Yes, the answer is yes, right? Because remember, what does it mean to be able, so I just do C1 times 1 plus C2 times x plus C3 times x squared, and this should equal 1 plus 2x plus 3x squared. Okay, what constants would make this happen? I mean, it's pretty straightforward. What would the constants be? What would C1 be? Yeah, 1, yeah, and then 1, 2, and 3, right? Pick C1 equal 1, C2 equal 2, and C3 equal 3. And I wrote it as a linear combination, right? Same thing, right? So just pick a arbitrary polynomial. A naught plus A1 x plus A2 x squared in P2. Can I write this? Can I write this as a linear combination of these guys right here? Well, yeah, right. So I would have C1 times 1 plus C2 times x plus C3 x squared, and this has to be equal to A0 plus A1 plus A2. What would my constants in this case be? Just A naught, A1, A2, right? C1 would equal A naught, C2 would equal A1, C3 equals A2. So no matter what polynomial I pick in P2, I can write it as a linear combination of 1, x, and x squared, right? So this thing, the set 1x and x squared spans P2 in this case, right? Again, so don't worry, if it's still not making any sense, we'll still do more examples. Let's see. What time is it? 45. Okay. Let's see. There's maybe one more thing I should mention. Okay, so this is our first theorem. So let's say 4.4.1. Span. Okay, so if S is a subset of V, where V is a vector space, then span of S is a subspace of, okay, so now not only is it a set now, right? Now it actually has a structure of a vector space. So remember, what does it mean to be a subspace? Remember, there's a theorem that says we check three things, right? Does it have a zero? Is it closed under addition? And is it closed under scalar multiplication? So you would have to check these three things to prove that span S is a subspace of the vector space V. Okay, so just, I guess I might just end class right now early, since there isn't really much else. But I have, because the other thing I have to talk about is going to take more than 3 minutes. But yeah, so I guess in summary, spanning sets are literally just like, if you think of them as pictures, you can just think of them as lines, planes, cubes, or higher dimensional kind of like objects, right? And they're all formed by linear combinations of that whatever I call whatever S is, right? Next time we'll talk about basis elements, which determines the dimension of the vector space. So this is how we'll define dimension for vector spaces, at least. All right, so that's it. Any questions in chat, possibly? Nope. Okay. Just what section is this? I think this is still week 6 and oh wait, sorry. Which section is it in the homework? What do you mean by that? Like what? Yeah, I'll send these out today. Don't worry. So this should be week 6 or 7. These two, what we talked about. Okay, so I'll see you guys later then.